Hi there, welcome to this video where we continue taking a look at the contents of Whitehead and Russell's Principia Mathematica. In this video I'm going to be taking a look at cardinal numbers and a little bit of cardinal arithmetic, particularly addition of two cardinal numbers. So we're going to be looking at mostly volume 2 in this video, although there is a little bit of volume 1 that I want to take a look at as well. The reason that I want to go through cardinal numbers is because there's a lot of nuance to this. How to interpret cardinal numbers, it's quite difficult in my opinion. It's very different and it's kind of unexpected. Cardinal numbers don't work necessarily in the way that we necessarily expect them to, in many ways. I spoke about cardinal numbers in another video, where I looked at cardinal numbers, cardinal arithmetic, and I looked at the proposition 1 + 1 = 2. In that video, I left out certain details. I didn't touch on certain aspects, but even that proposition 1 + 1 = 2 is not. Everything's not quite as it initially seems, even with that proposition, because of the way the cardinal numbers work in Principia Mathematica. Now, when it comes to that proposition, it turns out that 1 + 1 = 2 is it is always true in the system of Principia Mathematica. But when we take another proposition, for example, maybe 5 + 7 = 12, what we find is that this is only true in certain types. It's not necessarily true in all types. It can't be logically proved in all types. Whereas 1 + 1 = 2 can be logically proved in all types. 5 + 7 = 12 cannot be logically proved in all types. And the reason for this is because some classes in our hierarchy of types might not be large enough to account for certain cardinal numbers. Okay, so I spoke in my last video about types and the hierarchy of types and all that kind of stuff. And what I mentioned in that video, I think, is that we're only in a position to logically prove that the existence of at least one individual. There might be more than one individual, it's just that we can't logically prove it. And what that means is that if we are in the unfortunate situation where we do only have, say, one individual, or let's say we've got too few individuals, then the first kind of the types low down in the hierarchy of types will be typically too small to account for certain cardinal numbers. Okay, so that means that certain arithmetical propositions, which we might typically expect to hold, don't necessarily hold until we get sufficiently high in our hierarchy. So there is a little caveat with certain arithmetical propositions that we have to understand this proposition to be relating to types which are high enough in the hierarchy. So this video is going to be unscripted, as with my my most recent uploads. So there is a lot that I want to get through in this video that I hopefully remember to mention, but it's not necessarily going to be as polished as some of the videos that I've uploaded previously. So you'll have to bear with me if I need to think a little bit about what I want to say from time to time. I expect it's going to be quite a long video, so just to give you a bit of a heads up. If there are any questions that you have about anything that I mentioned in this video that I don't necessarily explain terribly clearly, then obviously please feel free to ask any questions that you have. I'm always happy to receive any questions relating to Principia Mathematica. I'm not an expert in Principia Mathematica. I've said before, I'll say it again. I'm not an authority on this. I'm just somebody that has a keen interest in Principia Mathematica. And all I want to do with these videos really is put my ideas and thoughts and interpretations out there, so that should there be anybody else in the world that's also similarly interested in Principia Mathematica, they can maybe benefit from my insights. It's not necessarily easy to find people that are interested in Principia Mathematica. And so hopefully my videos can, help one or two other people that are interested in Principia Mathematica. Hopefully my videos find those people and give them a bit of a nudge in the right direction. And also, if there's anything that other people that do know about Principia Mathematica and know it better than I do, they can give me some feedback and tell me potentially where I'm misunderstanding things. Okay, so we're looking at volume 2. There is an introduction to volume 2, Principia Mathematica, but my advice is don't necessarily feel that you need to have fully read and fully understood the contents of the introduction before you start to go through the main part of the work. Now, I'm not saying that the introduction is not important. It is, but if I compare it with the introduction to volume 1, what I've said in, I think, some of my previous videos with regards to the introduction to volume 1 is that if you're coming to Principia Mathematica from, as a blank slate, you don't have any experience, you don't have any familiarity with Principia Mathematica, then to try to read through the introduction in its entirety and expect to understand it is you're possibly expecting too much of yourself. My advice would be to read as much as you can before you start to feel a little bit lost, and then start on the main work. It's normal to, in my opinion, to get lost in the introduction because there's so many new ideas being thrown at you, and they're not completely, totally, and utterly, explained in their entirety in the introduction. It's better to work through the main part of Principia Mathematica and keep regularly checking in with the introduction. And in this way, you'll see which parts of the introduction relate to which parts of the main work, and you'll start to build a much better map of what's contained in the introduction and how it's relevant to which parts of the main work. And the same applies to the introduction to volume 2. Effectively, there's so much packed into the introduction. A lot of it won't make sense, in my opinion, until you've actually got a little bit of experience with the main parts, some of the main parts of the work, and even then it's cryptic. There's a lot of conventions, a lot of rules about how to interpret the notation in certain ways, and it is kind of cryptic, and it is something that you have to keep coming back to potentially, and reading and rereading in order to come to a decent enough understanding of. And I certainly don't fully understand all the nuances and aspects of the introduction to volume 2. Anyway, let's make a start then with cardinal numbers. And how do we get our head around cardinal numbers? So, okay, the notion of cardinal number in Principia Mathematica is bound up with a relation which was introduced in volume 1 in chapter 73, which is the relation of similarity. Okay, so SM. So if we've got two classes, alpha and beta, we say that alpha is similar to beta if there is a one-to-one correspondence between the members of these two classes. Okay, so one-to-one correspondence being for every member of alpha, of the class alpha, there is one and exactly one member of the class beta to which it corresponds, and vice versa. So for all intents and purposes, two classes are similar if they have what we might say the same size. Okay, in terms of the number of members. Obviously not physical size, but they've got the same size in terms of how many members they contain. Alpha and beta do not have to be classes of the same type. This gives a greater level of generality to the system of Principia Mathematica, but it does introduce a lot of difficulties which are dealt with in those first few chapters of volume 2. Okay. So you might argue, well, if it's simpler to just have alpha and beta of the same type, why not just do that? And my answer to that is that, as I've mentioned in a previous video, Whitehead and Russell are really interested in the greatest possible level of generality. However they understood that, that's seemingly what they're looking for. So if we don't need to restrict alpha and beta to being classes of the same type, then we shouldn't restrict them. And if that leads to a greater level of complexity, then so be it. That's just something that we're going to have to deal with. Obviously, if that complexity is insurmountable, it's demonstrably insurmountable, then that might force our hand a little bit, and we might have to say, okay, we're going to have to put this limitation on, otherwise we cannot overcome this obstacle. But it turns out that by allowing alpha and beta to be classes of different types, we get a greater level of generality, which is not insurmountable. We can kind of get around it in certain ways, but it's something that we can actually deal with. So if it's a level of complexity that we can deal with, then that's what we're going to have to do. Okay, so if alpha and beta are of the same type, then SM is what's called a homogeneous relation. And if SM is a homogeneous relation, this will give rise to what we will see as homogeneous cardinals. Okay, I'll be talking about these throughout the video. If alpha and beta are of different types, then depending on the relative positions of the types of alpha and beta in our typical hierarchy, we'll have SM will be a non-homogeneous relation, but if alpha is kind of further into the hierarchy than beta, or if it's a higher order, let's say, than beta, then we will get ascending cardinals. I hope I've got that the right way around. We'll find out anyway later in the video. And if it's the other way around, then we'll get descending cardinals. And ascending cardinals are not too bad to deal with. Homogeneous cardinals are nice to deal with. Descending cardinals there are certain difficulties. Again, not insurmountable difficulties, but certain difficulties that we've got to watch out for. And it's these descending cardinals that create a lot of the difficulties with regards to cardinal arithmetic. Okay, ascending cardinals don't really cause us too many difficulties. It's the descending cardinals that we've got to keep an eye on. So, once we've fixed our types of alpha and beta, then we can choose our class beta, and then we can find all of the classes of the same type as alpha, which are similar to beta. Okay, so we write this as this, and this is the cardinal number of beta corresponding to that type. But we've got a bit of a problem here, in that the notation that we use for our cardinal number of beta, it doesn't specify the type of it effectively makes a reference to this relation SM, but we can't tell from this notation what is the type of the domain of SM. Okay, so this is an example of what's called systematic ambiguity. This notation, these notations, SM and NC, they're both relations, but they have what's called systematic ambiguity. Okay, so there is an inherent ambiguity with these notations, in that when we talk about the cardinal number of beta, we cannot tell just from the notation NC primed beta which cardinal number of beta we're actually talking about, because the beta is going to have a cardinal number in each type. So I've spoke about this before, where I think maybe I haven't actually. So I'll talk about it now then. So in each of our types, we've got kind of corresponding concepts. So we might have, in each type, we've got, for example, a null class. Okay, because a type is a class. Each type in our hierarchy of types is a class. Okay, and to each type there corresponds a null class, but the null class corresponding to this type is different to the null class corresponding to that type. So a null class is a class with no members. So they're logically distinct, and we have to maintain that logical distinction between them. Okay, we have to maintain that logical distinction, even though psychologically they play the same role. A class with no members is kind of psychologically the same thing, whichever type we're looking at. But there is a logical distinction that we need to make. And similarly, when it comes on to cardinal numbers, so if we take the cardinal number 1, for example, there is a cardinal number 1 that corresponds to each type. There's a cardinal number 0 that corresponds to each type. And they're all logically different, logically distinct. Okay, so let's say the cardinal number of beta is 1. Well, which 1 am I talking about? Okay, this is systematic. This is the typical ambiguity of the notation. We can take typically ambiguous symbols and make them typically definite. And I'll have a look at that in a second, how we might do that. But very often what we'll see in Principia Mathematica is this typically ambiguous notation being used. And this brings with it certain difficulties. So, for example, we might see the same symbol being used to represent different objects in the same context. So, example, 1 plus 1 equals 2. Okay. This 1 here is the cardinal number 1 in some type. This 1 here is the number 1, the cardinal number 1, in a potentially different type. So each of these 1s is potentially corresponding to a different type. Okay, that, for all intents and purposes, logically distinct objects. Okay, it doesn't actually matter when it comes to the statement of this proposition which types, but we have to acknowledge that they are potentially referring to different types. And in some cases, it does make a big difference. So we might see something like, maybe I can choose an example. So let me have a look through volume, this volume. There are some quite early on, actually. Okay, here. Right, so this is proposition 100.511. So what we see here is that whenever the cardinal number of beta is an existent cardinal number, I'll be talking about that later in the video, what it means for a cardinal number to be an existing cardinal number, then Sm of the cardinal number of beta is equal to the cardinal number of beta. Okay, so in this we see this NC primed beta, the cardinal number of beta, coming up in 3 different places, but they don't all have the same type. In fact, they can't really all have the same type. It turns out that according to the conventions set out in the introduction, these 2 occurrences of NC prime beta are going to be of the same type. This is what's called a logical occurrence of this well, it's a formal. It's called a formal number. NC prime beta is called a formal number, and this is a logical occurrence, and this is a relational occurrence of that formal number, and this relational occurrence will be bound to this logical occurrence. So this is one convention IIT. No, sorry, convention IT in the introduction to volume 2. But that leaves this occurrence here, which is not necessarily the same as of the same type as these other two occurrences. For all intents and purposes, it is a different cardinal number in the sense that it belongs to a different type. It will be the same cardinal number, because the cardinal number 2, for example, in this type is really the same as the cardinal number 2 in that type. There's a logical distinction, but they're still kind of the same thing in many respects. So it's still kind of the same cardinal number, but it's in a different type. Okay, so these are some of the difficulties that we've got to grapple with. So what we can, in some contexts, we don't need to make these symbols typically definite. We can leave them typically ambiguous, and in that case, we need some conventions sometimes to tell us how to interpret, how to relate the different types together, how which types are going to be the same and which are going to be different, and things like this. It's all set out in the introduction. It's very cryptic. I don't fully understand it, but I'm getting there. So in some cases, we don't need to make these relation symbols typically definite. In most cases, it would be inconvenient. That there wouldn't be a convenient notation that we could realistically use that would be suitable. We just have to face the fact that we need to leave them typically ambiguous. In other cases, we can make certain typically ambiguous symbols typically definite. So this is set out in chapter 65 of Principia Mathematica, volume 1. So we can do this in the following way. So let's take a relation R. So this is, we're going to assume that this is a typically ambiguous symbol. What we can do is we can start to we can place restrictions. So let's say we've got a fixed object X, which is of a particular type. We can have R sub X, and this is the relation R with a domain limited to the type of X. Okay, and this is definition. So remember, a type is a class. So this notation is from section D of part 1. So when you've got things like limited domains and converse domains, so you might have something like this, for instance. T primed X is the type of X. It's defined in chapter 63, and it's a class. It's defined to be a particular class. We've also got Rx, which is R with the domain limited to the type of X. So it's almost like the type of X is, so if we've got X, which is a particular type in our hierarchy at particular level, the type of X is going to be the next level up, and the type of X will be the next level up from that. So what this is saying is that R sub X, the members of the domain of R are going to be of the same type as X, and R with the big X in brackets, that's going to be the members of the domain of R in this case are limited to classes whose members are of the same type as X. And then we can restrict the domain and converse domain. So we get R, X, Y, for instance. And this is R with domain limited to the type of X and converse domain limited to the type of X. we've got R with a big X, Y. This is R with converse domain, with domain limited to the type of X, and converse domain limited to the type of X. And then finally we've got R, X, Y. So this is R with domain limited to the type of X, and converse domain to the type of sorry, no, I've made a mistake. These should have been Y's. X and Y do not have to be of the same type. Importantly, they don't have to be of the same type. So we can apply this notation, for example, to SM. So we might have, for example, SM alpha beta. And what this would mean is that we've got the relation SM, and the members of the domain of SM are going to be of the same type as alpha, and the converse domain are going to be of the same type as beta. And this would correspond in that case to cardinal numbers. So the relation NC alpha, big alpha, small beta. Okay, because a cardinal number is a class of classes. Okay, so going back to the example that I gave earlier, if we've got the relation ASM beta, we can consider all of the classes of a particular type of the same type as alpha, which are similar to the class beta. So if the domain of SM has members of the same type as alpha, then the domain of NC that corresponds to this particular relation, the domain is going to be really limited to the type of alpha. Okay, and the converse domain is going to be limited to the type of beta, and hence we get this symbol NC, big alpha, small beta. Okay, so let's have a look at how do we define some of the how do we define cardinal numbers in a kind of intuitive sense? Well, the cardinal number 1 is defined to be the class of all classes, the class of all unit classes of a particular type. Okay, so class of all classes of a particular type. So there are symbolic definitions of these, but these are just intuitively how we think about maybe cardinal numbers. 2, it's the class of all classes of a particular type that have exactly 2 members. So I'm not going to write that, I'll just write exactly 2 members. 3 would be defined analogously, so this class of all classes of a particular type that have exactly 3 members. And in general, mu, which is going to be the class of all classes of a particular type which have exactly mu members. Now, mu doesn't have to be finite here. Oh, we've also got 0, which is the class, which is the null class. It's the unit class of the null class. That's maybe the best way for me to write it. It's the class whose only member is the null class. So that's not saying that 0 is equal to the null class. In fact, it's very important that we do not mistake 0 for the null class. 0 is the class whose only member is the null class. The null class, it turns out, in certain types will be a cardinal number, and it's kind of a degenerate sort of cardinal number, and it really messes things up in many respects. It's necessary for us to acknowledge it, but at the same time we try to avoid it in many contexts. But yeah, mu doesn't have to be finite, a finite cardinal number. This applies for finite as well as infinite. And we can straight away see that we've got certain problems here. So if our class of individuals does only have one member, so there's only one individual, then 2, the cardinal number 2, effectively, it's not that actually it doesn't exist. It's not an existent cardinal in our lowest type. What we'll find is that in our lowest type, because there are no classes in that lowest type, there are no classes with exactly 2 members. We've only got one individual. So we've got a null class and we've got a single class with 1 member, which is our individual. But we have no classes with exactly 2 members. And what that means is, in our lowest type, 2 is equal to the null class. Okay, in the lowest type. Potentially, that is on the assumption that there is only one individual. It might turn out, in reality, we might not be able to logically discern this. There might be more than one individual, there might be an infinite number of individuals, but there is the potential for our lowest type to be of insufficient size to account for the cardinal number 2, and hence it can't account for the cardinal number 3 or 4 or anything greater than anything other than 0 and 1. 0 and 1 we've got in every type. Okay, so what we can say then is that 0 and 1 are existent cardinal numbers in every type, but beyond that, we cannot assert that every that a particular cardinal number is an existent cardinal number in all types. Only in sufficiently high types. We can always, when it comes to finite cardinal numbers at least, we can always prove that there is a type high enough in our hierarchy where that cardinal number is an existent cardinal number, and hence any cardinal number, any type that is higher in the hierarchy will also be big enough for that cardinal number. But it doesn't, we cannot prove that cardinal numbers greater than or equal to 2. I know we've not defined order yet, but we know what we mean by order. Cardinal numbers greater than or equal to 2, we cannot prove that they are existent cardinal numbers in all types. Okay, so we can also make these are typically ambiguous symbols also, as I've already mentioned, right? So 0, 1, 2, 3, these are typically ambiguous symbols. We can make them typically definite if we need to. So that's also in chapter 65. So I'll just show if alpha is a class, or alpha is a symbol that we use as a typically ambiguous symbol to represent a class, we can define alpha sub x to be alpha logical product with the type of x. So for reasons of significance, if we take the logical products of 2 classes, they must be of the same type. So alpha here must be of the same type as the class which we call the type of x. And the types are classes. So I mentioned this in the previous video. Types are classes. So we can take the logical product of a type with a class, and that's what we end up with. So this is the class effectively whose members are of the same type as x. Okay, I mean it might be the null class actually. If it's the null class of x, it doesn't have any members, but it belongs to the same type as those classes whose members are of the same type as x. Okay, so this would be the null class for that particular type, even though it doesn't have any members. We can also have alpha x, which is alpha logical products of the type of x. This would be a class whose members are classes whose members are of the same type as x. Okay, so that's how we can fix the types of these of cardinal numbers, the symbols that we use for cardinal numbers, if we need to, although very often we won't do this. So the symbol that we use for the cardinal number 2, for example, we could fix it to a particular type, to x, for instance. And what this would mean is that this is the cardinal number 2 that corresponds to that type, which has the members of 2 would be classes whose members are of the same type as X. Okay, so this would be 2 type X, for example. These are used in some of the demonstrations. You'll see this kind of stuff going on more in demonstrations, really, in the demonstrations of the propositions, as opposed to in the statements of the propositions themselves. Okay, so let's have a look at some different types of cardinal numbers. In particular, initially, we're going to start out with homogeneous cardinals, because they're going to be the most useful type of cardinal number. What it turns out, we can homogeneous cardinals are always existent cardinals, so they're never equal to the null class, as we'll see. So what I'm wanting to do here is to just give some insight into how I personally might visualize cardinal numbers, okay, and the different types of cardinal numbers and how they work and things like that. So we've got SM, which is, we're going to assume that it's a homogeneous relation. Okay, so how shall I write this? So we've got some classes. We've got alpha, beta, gamma, and we've also got a null class corresponding to this type. So that's the converse domain. And in the domain, we've got all of the same classes, because it's a homogeneous relation. The domain and the converse domain are the same type, right? So this is of a particular type. Let's say so the type of some, which symbol shall I use? Delta, I don't know. And this is the converse domain of SM. And over here, we've got also alpha, beta, gamma, and our null class. And this is the domain of SM, and this is T, also T primes delta. Okay, so delta is some object of a suitable type. So then let's think about the cardinal number relation. So we've got our classes alpha. I'll just do alpha, beta, and the null class, for example. So over here, so that's the converse domain, and that is of the type of delta. And over in the domain, what we're going to have the good thing about this homogeneous similarity relation is that if we choose a class, there's always a class that's similar to it, namely itself. So we've got alpha, which is similar to itself. We've got, let's say, alpha sub 1, alpha sub 2, and so on. And this class here is going to be of the type of delta, but this is what we call the cardinal number of alpha. Okay. Now, if we wanted to be really precise about things, what we can say here is that these cardinal numbers, or this relation, is actually this relation, delta, delta, something like that. That would say that we're dealing here with these particular homogeneous cardinals. Okay. Now, this is okay. Sometimes we don't necessarily want to fix. We want to work with homogeneous cardinals, but we don't want to fix to a particular type. In that case, we can use this notation: N naught C. Actually, we will end up fixing this. I'll talk about that in a minute. So then for beta, we've got beta is similar to itself, beta 1, beta 2, and so on. So this is the cardinal number of beta. Or more specifically, we could say that this is n0 c primed alpha and this is n0 c primed beta, to emphasize that they are homogeneous cardinals. And then the null class, the only class that's similar to the null class is the null class. So this is effectively 0. Okay, n0 c primed null class, which happens to be equal to 0. Okay, so what we find is that in the homogeneous case, all of our cardinals, any class that we choose to find, we can find the cardinal number of any class in that type, and all of the should I say, yeah, we can find the cardinal number of any class in any type anyway, but the cardinal number corresponding to that type will be an existent. We can guarantee that it's going to be an existent cardinal number. Existent in the sense that the class that represents that the cardinal number of that class has at least one member. Generally speaking, it'll have more, but it's going to have at least one member. Okay, so that's the homogeneous case, and that's nice and easy. It's a really nice case. We'll find that homogeneous cardinals play an important role. So let's have a look now at the case where we've got a discrepancy, a non-homogeneous SM, similarity relation. So SM. And let's say we've got, in this case, in the converse domain, again, we've got beta. Okay, how shall I, right, let's do this. Beta 1, beta 2, beta 3. We've also got a null class. So let's say that this is the type of beta. Okay, we've also got a null class, and to emphasize that it is a null class of the same type as beta, I'm going to write this, the logical product of the null class with beta. And then over here, we've got all of our alphas, alpha 1, alpha 2, alpha 3, and so on. And we've also got a null class, and this is the type of alpha. So let's assume in this case that alpha is of a greater order. The type of alpha is greater than the type of beta, so to speak. So alpha, the type of alpha is, inverted commas, greater than the type of beta. Okay, so what happens in this case? Well, in this case, with our cardinal numbers, let's say we've got beta 1. We've got classes alpha 1, 1, alpha 1, 2, alpha 1, 3, for example, that are going to be similar to beta 1. Okay, because the way that types are constructed, if beta is of a lower type than alpha, then in the type of beta, for any class that we choose in the type of beta, there will be a class in the type of alpha that is similar to it, but not the other way around. And this is where we're going to get some of our difficulties, okay? Particularly when it comes onto the next case. So, I mean, this is all proved rigorously in Principia Mathematica, so I'm just giving an intuitive, informal perspective on things here. So this is all proved in Principia Mathematica. So then we've got beta 2. We've got classes alpha 2, 2, alpha 2, 1, sorry, alpha 2, 2, alpha 2, 3. So this is going to be the cardinal number of beta 1. This is going to be the cardinal number of beta 2. And we've also got the null class. Well, we've got the null class here as well, but it's the null class corresponding to alpha. So that's the cardinal number of lambda beta, which again is going to be equal to 0. Okay, so this is the converse domain of this relation, and that's of type beta. The domain of this is going to be of type, the type of alpha. Okay, so this relation NC, we can describe it more accurately, or more definitely, let's say, as alpha with a little beta here. Okay, so arguably this could also be written as NC alpha beta primed beta 1, for instance. That's if we wanted to fix the type of this relation. But we do have a little bit of a problem here, in that there are also classes of the same type as alpha which don't are too big effectively. There's no class in the type of beta that's similar to these classes. So outside of all of these cardinal numbers, we've got some other classes that are kind of floating around that are too big to match up to anything in the type of beta. So we've got kind of this excess in the domain here. Not all of the members of the type of alpha are going to be in a cardinal number. Okay, so we've got this kind of overflow. So this is one way that we can get a kind of mismatch between within our cardinal numbers. Okay, so but notice that for every cardinal number, for every class that we choose in the converse domain of this NC relation, we can find its cardinal number, and its cardinal number is an existent cardinal number in this case. Okay, so this would roughly correspond to, now I'm doing this slightly differently to how it deals with ascending cardinal numbers in Principia Mathematica, but these are effectively ascending cardinal numbers that we're looking at here. Okay, so then let's have a look at the other direction. So if we've got SM, and again we've got beta 1, beta 2, beta 3, and we've also got the null class. This is the converse domain, and it's of type beta. And over here we've got alpha 1, alpha 2, alpha 3, and the corresponding null class. And this is of the type of alpha. So in this case, we're going to assume that the type of alpha is less, and I'm putting that in inverted commas because it's a bit of a vague. I'm using it in a kind of vague sense, imprecise sense, but sufficiently descriptive for what we're doing here. The type of alpha is less than the type of beta. Well, okay, so now in this case, again, we can make this relation typically definite by writing it as, again, alpha beta. But in this case, we've got other things going on. So we've got beta 1 as one possibility, beta 2, and then we've got the null class. Okay. So this is the converse domain. This is of type beta. But what goes on now? Well, if beta 1 is of the right kind of size, then we can find classes over here, alpha 1, 1 alpha, 1, 2 alpha, 1, 3, that are similar to beta 1. Okay, and this will be the cardinal number of beta 1. The null class, that will be similar to the null class in the type alpha. So that's the cardinal number of the null class corresponding to beta, which is going to be equal to 0. But then let's say beta 2 is too big. Well, there's going to be no classes in the type of A which are going to be similar to it. So in other words, this is the cardinal number of beta 2 in that case. Cardinal number of beta 2 is equal to the null class. We must make a distinction between the null class in this type is the type of beta, type of alpha, t primed alpha. So this here is the null class. Oh, get rid of that. The null class corresponding to that type. Okay. However, this class whose member is the null class of the type of, this is a different thing. We must distinguish between these two. So what we see here is that if in this case, if the type of the converse domain of our SM relation is higher in the hierarchy than the type of the members of the domain, then some cardinal numbers, some classes have non-existent cardinal numbers. Okay, in other words, their cardinal number is equal to lambda. Okay, that's still a cardinal number. It's just it's non-existent. Non-existent in the context in the sense that it is a class that doesn't have any members. So remember that in Principia Mathematica, an existent class is one who is a class which has at least one member. The null class is still a class, but it's not described as an existent class. It's because it doesn't have any members. So it's not an existent class. Okay, so that's how we can view things when we've got that the discrepancy that way around. And then there are cardinal numbers that are of relation type. I'm not going to get into that, to be honest with you. But this is how I personally visualize the different cases with the cardinal numbers. And this really helps me to figure out sometimes what's going on, particularly when we're dealing with ascending cardinal numbers and things like that. Okay, so hopefully that makes some sense. But it's this case where we've got cardinal numbers equal to the null class where we start to get some of our difficulties. So this video's it's gone on quite a bit already. So let me jump onto cardinal arithmetic, and let's take something like 2 plus 3 equals 5. Okay, or 2 plus 3. Oh, in fact, I'll tell you what. I've done this in a previous video, so I'm not going to go through all of the details again, but I need to state the definition of how to add two cardinal numbers, how we add two cardinal numbers together. So if we've got mu and nu, this is the class of xi. I want to say xi. The class of xi's such that there is an alpha and a beta, such that alpha is equal to, mu. Mu is equal to n naught c primed alpha. Notice that we're using homogeneous cardinals here, right? And nu is equal to n naught c primed beta. And psi is similar to So this was the class sum, arithmetical class sum, which I'm not going to go into detail about here because I went through this in one of my previous videos. So this is how we define the addition of two cardinal numbers. Now, there's some things that I need to talk about here, namely that this is what's called a formal number. Okay, mu plus nu is called a formal number. This is explained in the introduction to volume 2. I'm not going to get into what formal numbers are, but this is a formal number, and it has what's called an actual type. Okay, but each mu and nu here are cardinal numbers. These are the components of this formal number. These are cardinal numbers. They each have a type. They don't have to be of the same type, right? And they're called the subordinate types of this formal number, mu plus nu. So mu and nu, the types of these are the subordinate types. And the subordinate types do not determine the actual type. The actual, this formal number is a typically ambiguous symbol. Okay, even when the subordinate types are typically definite, the actual type of this formal number is still not determined. Okay, and also all we can say is that the actual type of this formal number, mu plus nu, must be the same as the type of this class over here. Okay, but both sides have typical ambiguity. But because of the equals sign, they must be of the same type, right? So, if we take, for example, 2 plus 3 on the one hand and 5. So it might be in a certain type. The type that we choose for 2 is what's called adequate. In that case, for a particular cardinal number, a type is adequate when the cardinal number in that type is an existent cardinal number. Okay, presumably, I don't think the authors use inadequate, but if that cardinal number is effectively equal to the null class in that type, then that would be an inadequate type. So the problem that we've got really is when we've got a formal number like this, if one or more of the subordinate types is inadequate, the actual type, it doesn't make any difference. The actual type can be inadequate, but the subordinate types need to be adequate. Okay, so let's just have a look. If the let's say we choose a particular type for 2 and it's adequate, so the 2 looks like what we expect it to look like. But in the type that we choose for 3, it's inadequate. Okay, it's an inadequate type. Then what we get is 2 plus, effectively 2 plus the null class. Well, if we refer to our definition of cardinal addition, what we find then is if mu is equal to the null class, is it mu is equal to the, yeah. Remember, all homogeneous cardinals are existent cardinals. Well, if mu here is the null class, then we cannot find a homogeneous cardinal that is equal to it. Right? So in other words, our mu plus nu, our class of psi, is going to be the null class. So this is effectively going to be equal to the null class, right? But now this is a typically ambiguous symbol. I can choose the type of this, right? So I choose the type of this. It doesn't matter which type I choose. It's always going to be equal to the null class. However, if I go high enough in my hierarchy, 5 I can find a type which is adequate for 5. And 5 looks in that type how we expect it to look. In other words, the class of all classes which have exactly 5 members. So 5 is what I expect it to be, but it's not equal to the null class. So in other words, if one of my subordinate types in my when I'm trying to add two cardinal numbers together, if one or more of the subordinate types is inadequate, then this 2 plus 3 does not equal 5 effectively. It's not forced to equal 5. It fails in low enough types. So there's a little caveat for this to work. For me to say 2 plus 3 equals 5, this has to be on the understanding that the type that I choose for 2 and the type is adequate, and the type that I choose for 3 is adequate. They don't have to be the same type, but they just have to be types that are adequate for each of those particular cardinal numbers. And then, even if I choose for whatever I get for this sum, if I choose a type for the actual type which is inadequate, it doesn't make any difference then, because what I get is that both this and this will be equal to the null class in that type, so I get equality. Right? So, and I mean, as long as all of the actual type is adequate as well, then I get 2 plus 3 equals 5, just as I expect. But this also applies to 1 plus 1 equals 2. Right? Now, it turns out in this case that every type is adequate for 1. So we've got no problems here with inadequacy of types. These ones are never going to be equal to the null class. However, it might be that the actual type that I choose for this expression here is inadequate. If I choose the lowest type, it will be inadequate. In other words, it will be that. But it doesn't matter, because this will also be equal to the null class, because they'll have to be of the same type. The actual type of 1 plus 1, for this equality to be significant, will have to be of the same type as the 2. They will both be equal to the null class. So I still get 1 plus 1 equals 2, even though I might end up with effectively the null class is equal to the null class. But that's fine. They're still equal, right? But this is how arithmetical propositions can fail in the system of Principia Mathematica, and it makes a right mess of some of the propositions. It's just one of the things that you have to deal with as you go through. There are certain conventions, such as convention AT, I think it is, on page 31 of the introduction. All equations involving pure arithmetical formal numbers are to be arithmetical, in other words, non-null. Okay, an arithmetical formal number is the ones that we've been looking at are examples where you've got arithmetical formal numbers are ones that involve addition, subtraction, multiplication, or exponentiation. They're arithmetical formal numbers. Pure arithmetical formal numbers are ones that involve either constant formal numbers or I can't remember now off the top of my head. They don't involve relational formal numbers. So SM double primed alpha, which I wrote earlier on, that's a relational formal number. So pure arithmetical formal numbers will not include those. And to say that all equations involving pure arithmetical formal numbers are to be arithmetical means that they're non-null. Okay. So that just gives a bit of insight into how I personally interpret cardinal numbers and things like that. What I didn't look at really was classes of cardinal numbers so much. we can have the class of homogeneous cardinal numbers. Now this again is a typically ambiguous symbol. We can make it typically definite by writing something like this, and that will correspond to those homogeneous cardinal numbers corresponding to the type alpha, whatever. This is defined to be so NC it's a class. It's a class of cardinal numbers. It's defined to be the domain of NC. So in particular, we get N0C, which is the domain of N0C. But remember, these are typically ambiguous symbols. So this doesn't pick out a particular relation as such. It's all kinds of possibilities, but we can make things typically definite. There is an additional difficulty that we get here, in that for this class, if we want, sorry, not that notation. I know I'm rambling a bit here, but it's whatever. So this NC, to make this fully definite, we can't just write NC alpha here. To make it fully definite, actually, we need to refer this to, we need to make a reference to the converse domain of the relation that this is kind of derived, that this class is derived from. And so we can write a beta in there. That tells us about the type of the converse domain. This is all gone through in more detail in here. It's quite complicated. I mean, it's necessary. You've got to get your head around it, and you do kind of get used to it, but it is quite complicated. And I've in no way done it justice here. There's loads more that I could say about this, but the video's already gone on for long enough. So I'm actually going to leave it there. I think I've said pretty much everything that I want to say for this video. I'm sure there'll be plenty of questions that people will have about this. All I can suggest really is to get the full picture. Really, you've got to read Principia Mathematica yourself, and spend the time with it. What I say in these videos is really just the tip of the iceberg, and hopefully it does help people somewhere, or it might motivate some questions. Motivate you to prompt some specific questions that you want to ask. Please feel free to ask any questions that you want to ask. Okay, so I'm going to leave the video there. Please give it a thumbs up and a nice positive comment in the comment section. In the description to this video, I will leave a link to my Buy Me a Coffee page. It's a bit late in the evening for me to be having coffee, but I do like coffee. And I would be very grateful for any donations that you're able to make. And I do stress that if you're able to make a donation, if you're not in a financial position to be giving away, to be donating money and things like that, and please, don't be feeling that obliged to make a donation. And only make a donation, obviously, if you think it's my videos are worth it. But I'm going to leave it there. I plan to make some more videos, plenty more videos on Principia Mathematica. I've got so much that I want to say about it, looking at it from different perspectives. If there is anything in particular that you want me to make a video on, then please let me know. But with that, I'll say thank you for watching, and I will see you in the next video. Goodbye.